and generate photons the same as incident signal photons. In this way, photons in the signal light are increased and the signal are continuously amplified when traversing the EDF. So that's how EDF amplify your signals. So let's check the EDF structures. See the structures. We have input port, output over here, and we will have two different TAP over here. These two different TAP is used to split a little part of light from your main path to do the detecting. Okay, and it will detecting the input power and detecting the output power over here. Then we will compare the output power, input power. Then we will got the gain of this EDFA, right? Use output power minus input power. We will got the gain of this amplifier. Okay, and we will have two isolator over here. This two isolator is to reduce the reflection light. These two isolated over here is to reduce the reflection light. Okay, and then we have a Cooper over here to mix the bumping laser light and your service light together and transmit into this erbium doped fiber. In this erbium doped fiber, the service will be amplified. So let's check the EDFA features. You can see the advantage of our EDFA is our EDFA is consistent with the minimal attenuation windows of single mode fiber, which is 50-50 nanometers. Okay, and it has a high energy conversion efficiency, right? And it has a high gain. That gain could be 36 dB. Okay, and the low noise figure and high output power because the gain is very high, so we can get high output power. Okay, and it has good gain stability, right? But for the disadvantage of our EDFA, it has fixed gain range. It only amplifies 50-50 nanometers. It cannot amplify other wavelengths. That's also why our WDM only use 50-50 because EDFA only amplify 50-50 nanometers, and we are use EDFA a lot in our WDM network, so that we limit it. We cannot use other wavelengths, right? And the second advantage is gain on flatness.
The gain bandwidth of EDFA is large but not flat. What does it mean? Actually, when we input a lot of different wavelengths into EDFAs, actually EDFA cannot give every wavelength the same gain. Maybe some wavelengths gain is a little higher, some wavelengths gain a little lower. Not too much different, okay? Just a little different. But that's also make if we have a lot of different EDFA cascading together, that will make, after you pass through too much EDFAs, that make your optical power unflatless. So that's, we call it gain unflatless. But don't worry, we already use EDFA for a long time, right? So actually we already discovered some new technology to fix these problems. Okay, so we have some special technology used to fix this. Okay, the last disadvantage of our EDFAs is optical surge problem. So what is the optical surge problem? Okay, the input optical power can be increased quickly using EDFAs, but the dynamic gain of the EDFAs change slowly. Therefore, the optical surge problem may occur in case of step change of the input signals. That is, an input optical power peak occurs. The optical surge problem is more severe when EDFAs are cascaded. The peak optical power can be several watts, which may damage optical to electrical converters and optical connectors and phases. So that is the optical surge problem. Okay, it will maybe affect your service quality and maybe affect your hardware quality.
Okay, so that's the disadvantage of EDFA. Actually, we have a technology being used. EDFA is this one, automatic gain control AGC functions.
So what is AGC? Why we did this one? Actually, simply we can talk about it simply. That is, AGC is used to control the gain, like its name, to lock the gain of EDFA. Okay, because the gain locking of an EDFA is a very important issue. as a WDM system is a multiple wavelengths working system. If the signals of certain wavelengths are lost or added, the energy of a WDM system is shifted to the signals that are not lost due to gain competition. Okay, check this out. If, for example, in the first stage, we only have one wavelength being used to amplifier, so then we can control the gain of this one wavelength. But suddenly we add a lot of wavelengths into your fiber, so we must control every wavelength still has the original gain, didn't change the power, change the gain. Actually, just like we have a lot of wavelengths now, but suddenly some wavelength is lost. Okay, so we also need to control this one wavelength gain didn't change because if the signal of certain wavelengths are lost, like I already said, the energy of WDM system is shifted to the signals that are not lost due to gain competition, right? Thereby increasing the power of other wavelengths at the receive end. The sudden level increase may cause bit errors. In extreme case, if 7 of the 8 wavelengths are lost, all the power will be centralized on the remaining wavelengths over here, and the power may reach about 17 dB. That is very high. Okay, this will result in a strong nonlinear effect of all the receiving power overload of the receivers, as well as larger numbers of bit error, and maybe the hardware will be affected. Okay, the hardware will be broken or something, right? It's pretty dangerous for these problems. Okay, so actually we have some technology for locking the EDFA gains. The typical method is to control the gain of the bumping laser. How do we control it? You can check this one. We have an internal monitoring unit of EDFA controller the output of the bumping source by monitoring the radio of the input power over here to the output power over here. So you can check this hardware. We have a split over in the input port and a split in output port. This two split is used to split a little part from the main path to do the texting. To text input power is which value and output power is which value. Then we can know how much gain we give to this service and send it to DSP to do the math calculation. And which kind of math we will do over here is this one. Gain equal to P out to P in. If we find out the gain is too high, so this one will control the bumping source. Okay, to increase the bumping source power or decrease the bumping source power depends the gain is too high or too low, right? So that's how do we control the gain. Automatic gain control function is being realized like this way.
Okay, so we are finished about the EDFA. Let's see another very important amplifier, Raman amplifier.
Okay, so why we call it a Raman amplifier? Because we use a Raman nonlinear effective. So what is Raman nonlinear effect? That actually in a common optical fiber system, the optical power is not very high, it's low, and the optical fiber has nonlinear transmission features. So with the incident optical power of light into the fiber is rather high, like this way. The power is very high. The high energy bumping light scatter to transform a small portion of the power to the beam whose frequency is downshifted, like this arrow, and is almost around 13 THz, and this width is almost 30 nanometers. Okay, so this we call it Raman effect. And why we can like this way? Because over here you have a lot of energy over here. At this time, if this arrow is your wavelength arrow, okay, so your service wavelength pass through this arrow. Okay, so the energy will be increased because we have a lot of energy in this arrow, right? So that's how do we increase the power of your service by this Raman effect. Okay, but the common Raman scattering requires very high laser power. this bumping source power should be very high. Okay, actually, when we have the Raman effect, the gain peak is around 13 THz that the bumping light frequency is downshifted. Okay, so actually we can control the frequency of this bumping source. Then we can control the gain error. So actually, principally, we can use this Raman amplifier to amplify any service. 3010 nanometers can be amplifier, 5050 can be amplifier, right? So at this time, this is advantage of our Raman amplifier. We can controlling the frequency for the bumping source to control the gain error to realize any wavelength amplifier. Okay, that's the advantage of our amplifier. Okay, but we also have some disadvantage, because if you want to have Raman effect in your fibers and to amplify your service, you must have a very high bumping source power. Okay, and it will request a very good laser, very high energy. Okay, so that will be very hard to maintenance for your board, for your hardware, and it will be very expensive to realize this kind of amplifier, right?
So the features of our Raman amplifier, you can see the advantage: flexible gain range. We can change the bumping laser to change the gain error, right? And a simple structure. We don't need a special fiber, urban doped fiber. We don't need it. We just need a normal fiber, G.652, right? And it uses the nonlinear effect. Okay, the noise is very low. Surely, Raman amplifier has a lower noise than EDFA. EDFA has very high noise, right? Okay. So about the disadvantage of our Raman amplifier, he need to use high bumping power. We must put a very high power into the fiber, then we will have Raman affected. If we don't have it, we cannot use Raman amplifier, right? And it has a long energy conversion efficient, right? So it needs very high energy, but it only give your service 10 dB yen. That is very high cost, right? And waste too much energy for Raman. But the noise is very good, right? So that's the big advantage of Raman amplifier. Okay, so you can compare the Raman amplifier with EDFA. You will find out those two amplifiers must have very big difference between these two amplifiers. For example, EDFA fixed gain range, right? Only 50-50 nanometers. But Raman flexible gain range. Any wavelength can be amplified, right? The EDFA very complicated structures. The Raman simple structures. Okay, EDFA high noise are Raman amplifier no noise, low noise, right? And the Raman amplifier can give you service very low gain, only 10 dB. But EDFA can give you service very high gain, right? And the cost is not very high in EDFA, but the cost is very high for Raman amplifier. There will no need too much energy to make EDFA running, but we need a lot of energy to make Raman amplifier has Raman effective, which is a long layer effective, right? So that's almost big difference between Raman amplifier and EDFA. So when we use the EDFA, when we use the RFA, actually, EDFA is being widely used in our real network. But for very long distance transmission, you need to consider about the noise in your network. If the noise too much, the service will have too much error. At this time, you can use Raman amplifier to replace some EDFA in your network to realize very long distance transmission, right? So that's the application of our amplifier. Okay. So let's see, depends the location we used for the amplifier. We have three different places can use the amplifier, which is south station, sink station, and middle station. Okay, and the light station. In three different places, the station has different name. South station we call it the post amplifier. The sink station we call it pre-amplifier, and then in the light station we call it line amplifier. Okay, they are both the EDFA. Okay, they are you all into three different places. Actually, in three different places, we have different requirements about the EDFA. For example, in South Station, in this station, everything starts from south. So for this kind of amplifier, we need its gain should be good. And the sensitive for this amplifier, no need very good. But for the preamplifier, the service I received is